Hello, everyone. So for the last couple of hours, we've discussed how to plan and schedule a project. And today we are going to talk about crashing the project. So first, let me share my screen. Okay. So what is crashing in a project management? The crashing a project in the project management is a methodology used to speed up project timeline by adding additional resources, of course, without changing the entire scope of the project. And those additional resources could include the extra labors to a certain task to finish it more quickly, or it could involve paying some extra, paying a premium for a faster result, okay? And there are projects happening all the time, all around us, almost daily basis. And, no matter how much time and attention you pay to plan for your project, in reality, projects frequently run into some sort of problems or might need to be speed up because of a range of reasons. So for example, you might need to start over a certain tasks, certain activities because of lack of quality performed and mismatching of the expectations and the sort of problems with coordinations, things like that. And there might be some external factors that you have no control. For example, if you know one of your competitors, the product is scheduled to hit the market before your planned product completion time. And if you don't speed up the process of your own project, then you could lose the competitive edge over them, right? And any other unforeseen circumstances could also pops up. So for example, during the middle of project period, if you know that if there is a huge penalty for failing to meet a project completion deadline, then putting some additional cost could be justified to an extent, right? So that's where the project crashing comes in. So earlier we considered this example. So in this example, the manufacturing company is about to introduce the new product, what is called the product number 3. And so basically 1 unit of product number 3 is produced by assembling 1 unit of product number 1 and 2, right? So this is product number 3. And the list of activities associated with the introduction of this product number 3, and together with the estimated duration and the immediate predecessors all given in this table, right? So the project network diagram, the activity on ARC, AOA network diagram can be constructed like this based on this table information. And the node number 0, event number 0 is the beginning of the project. And down here, node number 5, that represents the completion of the project, right? And also we talked about the dummy activity is needed in this case to ensure that these two nodes, node number 0 and node number 2, cannot be connected by more than one arc. All right. So in this case, it's really easy to see that the critical activities include A, D, and E, and F. And the critical path is going to be 0, 2, 3, 4, 5. And in this case, the length of the 12 days required to complete the entire project. Okay, now we are going to talk about how to build up the linear programming model for determining the allocation of the resources, which can minimize the total cost of meeting the new project deadline. So let's suppose that one of your competitors begins working on a very similar project, and as of now, highly likely your product is going to hit the market, let's say within a week, which means that you must finish your project at least within the next 6 days, one day before your competitors, the final product hit the market. Okay, and the good news is you have some additional funds available to be allocated for this purpose to meet the new deadline of 6 days. Okay, so based on the internal source of information, if you allocate the additional funds to certain activities, then you can actually reduce the duration of any activity by as many as 2 days. Okay, so those are the given information. And this table shows the daily crash cost for each activity. So that's going to be the unit cost of reducing the duration of each activity. Okay. Okay. So I want you to recall when we construct the primary LP to obtain the shortest completion time for the project, right? We define the decision variable y sub I represents the time that each event I occurs. And for the crashing problem, we also need to define another set of decision variables. So let's say R sub K stands for the changes in the amount of time in each activity K. So that's actually, in our case, the reduction in the duration of activity K, right? So for example, if I say R sub A, then refers to the reduction in the duration of activity A, right? Then using this new set of decision variable, we can construct our objective function. That's going to be the minimizing the total cost of meeting the new deadline, right? So using these table values, crashing cost values down here, that's going to be minimize $1,500 times R sub A plus $2,500 times R sub B plus $2,000 times R sub C and so forth until $3,000 times R sub F. Okay. Okay, then what constraint do we need? Because we know that by allocating these additional funds to an activity, the duration of each activity can be reduced by at most 2 days. So we will have an inequality constraint for every activity, A through F, right? Like this. R sub K has to be less than equals 2 days. Okay. So we will have 6 of these constraints, one for each activity, one for each arc in the project network. Okay. And what other constraints do we need? So for every precedence relationship, we will have a new set of inequality constraint. Okay, that's going to be y sub j is greater than equal to y sub I plus d sub ij minus r sub k. So for example, event number 0 must precede event number 1 translates to y sub 1 is greater than equals y sub 0 plus 4. That's going to be the duration of activity B minus the reduction in the duration of activity B, right? So that's because activity B now has a duration of 4 minus r sub B, right? So y sub 0 plus 4 minus r sub B is going to be the completion time for activity B. Is that correct? So for every directed arcs in this AOA network diagram, we will need an inequality constraint like this. Okay. And last but not the least, we need one more constraint that ensures that the project is completed within the new deadline, within the 6-day deadline, right? So we need y sub 5 minus y sub 0. That is the project completion time, right? Has to be less than equals 6 days. Also, we need to add sign restriction for every decision variable. And for our new decision variables, r sub k, we just need non-negativity restrictions. But as before, y sub I has no sign restriction because y sub I is the each event, the start time of each event. And each event can begin at any point in time, in the past, present, or in the future, right? So the decision variables, y sub I, can take any positive and negative real values. So you need to specify these restrictions, okay? Okay, so putting all together, this is the complete LP model for crashing the project. Okay, so let me open up Lingo so that we can get the optimal solution. Okay, let me disable my camera. Okay, so, and also I need to make sure the current window is for Lindo or Lingo input. So it does say Lingo model. So I'm gonna use Lingo input in this case. So I'm gonna copy everything. And paste down here. Oh. Yeah. Okay. Okay. Just for the easy readability, just sort it out in this way. Okay, first thing, Lingo does not recognize the word minimize. So we have to use min instead of minimize, right? See, right after I put the space here, the colors of the words change it to blue. That means Lingo recognize this keyword. And then I'm going to put the equal sign. And Lingo does need asterisk as the multiplication symbol, right? So I'm going to put them in here. And I'm not quite sure if Lingo does recognize the subscript. This original input was made from the Microsoft Word. So let me just leave it as it is and see later. So we do need semicolon. And we don't need subject to or st, right? So now I'm gonna change this comma with semicolon. Okay. We also need semicolon down here. Both Lindo and Lingo doesn't need sign the non-negativity restriction. So I'm gonna just remove this, but we need to specify unrestricted and sign for every y variable, and Lingo does use syntax at free, right? Inside parentheses, you need to specify the variable name. So that's going to be y sub 0 through y sub 5, right? So I'm going to just copy here. Okay. And then I'm going to just copy paste down here. And then change this 1, 2, 3. Okay, let's just see what happened later. And then we do need, okay. It's gonna be a good practice. I never use the regular font with subscript for Lingo input. So let's see how Lingo responds. So did I miss anything? Okay, so let's run it. Oh, okay, I got it. Lingo does not recognize the symbol, so I need to change to less than equal, like this. So I need to replace all of this. And one more down here. Likewise, this has to be changed to greater than equal sign. So, okay, we are almost done. What else? Okay. I believe this time it's gonna work. Let's see. Oh no. What is wrong? 4 minus. Oh, maybe. Okay, so let me just retype minus symbol. Okay, yeah, that's different because I got this formulation typed in Microsoft Word. So some of these symbols cannot be recognized by Lingo. So even this, I'm gonna change. Let's see. Okay, yeah, it's working. Great. Okay, so we've got the optimal solution down here. So can you see that? Let me zoom in. So this is our optimal objective function value. So based on that, the project deadline of 6 days can be met for an additional cost of $15,500. Okay, that's what the optimal objective function value tells us. Okay, and for the optimal solution, you need to go down here and then look at these new variables values, R sub A through R sub F. So this optimal solution tells us that the duration of these activities A, B, C, D, E, and F, have to be reduced by 2 days, 1 day, 1 day, 2 days, and 2 days, respectively. Okay. So let me open Microsoft Word. So let me redraw the AOA network diagram. So we have 0. I don't need to. We're gonna just copy from our PowerPoint slides and then paste it down here. Okay, so that's the original AOA network diagram, right? So according to our optimal solution from Lingo suggests us the activity A has to be, the duration of activity A has to be reduced by 2 days, right? So it's going to be 3, right? Likewise, the duration of activity B has to be reduced by 1 day. So it's going to be 3. And C is going to be 2, 3 minus 1, right? D is going to be 2 minus 2. Now it becomes 0. E is, okay, no changes. And F is reduced by 2. So it's going to be 1, okay? So after reducing the duration of the activities A through F by the given amounts from this optimal solution, you obtain the new project network diagram like this, okay? And so I can verify that the project deadline of 6 days can be met. For a cost of this $15,500. So let's do that. So based on this new project network diagram, let's build up the primary LP model so that we can at least obtain the project completion time, right? Minimum project completion time. So that's going to be this. That's the objective function, if you remember, right? For the primary LP. And we don't need those, right? This is going to be redundant. And instead of those R values, I'm going to use these optimal solution values. So for RA, it's going to be 2. RB is going to be 1, right? RC is 1. RD is 2. RE is 0, right? And RF is 2. And we don't need this, right? That's the primary LP that we talked about earlier, right? So let's run it. See here? With this updated network diagram, we can complete the project within 6 days here, according to the optimal solution, primer LP, right? And of course, if you want, you can construct dual LP to obtain the detailed information about the critical activities and critical path. So let's do that because these are small network diagram, so we can easily build up the dual LP. Dual LP is the maximization problem. We want to get the longest path from the start to finishing node, right? So that's going to be 3 times x02, right? Plus 3 times x01 plus 2 times x24 plus am I doing correct? 2 times x34 plus x45, right? I forgot asterisk is the multiplication symbol. Okay, that's our objective. So I missed equal sign. Okay, and if you remember the constraints of the dual LP, so the conservation of flow equations for this AOA network, right? And the left-hand side of each constraint is going to be inflow minus outflow, right? For each event, for each node. So regarding the node number 0, event number 0, there is no inflow, but we have 2 outflow, right? So that's going to be inflow minus outflow equals net flow, right? So for event number 0, that's going to be negative x01, x02 equals -1 because the event number 0, the node number 0 is the supply node, right? For event number 1, we have 1 inflow from node number 0, so x01, and we have 1 outflow goes to event number 2, so x12, right? Equals 0. And for event number 2, we have 2 inflows, x01, x sorry, it's x02, right? And 1, 2 minus x23. And for event number 3, 1 inflow, x23, 1 outflow, x34. And for event number 4, we have 2 inflows, x24, x34, and we have 1 outflow, x45, 0. For the finishing node, we have only 1 inflow, but no outflows. And node number 5 is the demanding node, so the net flow amount has to be +1. And I forgot semicolon at the end of each constraint. What else? And the negativity restrictions doesn't need to be added. So I'm going to just put ending mark here. So let's see. Okay, so these are the optimal solution from our dual LP. And this dual LP tells us the critical path is going to be 0, 2, right? Because of this. And then 2, 3, 3, 4, and 4, 5, right? So this is our critical path, 0, 2, 3, 4, 5. These are our critical paths. So the critical activities does include A, D, E, F. A, D, E, and F. Those are the critical activities. And the project can be completed within 6 days, right? So in this way, we can verify the project deadline of 6 days can be met for the cost of $15,500. Okay, does that make sense? Okay, so let's go back to our presentation slides. Okay, so let's consider to solve this problem. Okay, so I've got this example problem from the Hillier and Lieberman operations research textbook with some modifications. So let me give you about 10 to 15 minutes. Why don't you pause the lecture video and read through the problem description, and also think about how to formulate the LP model that we discussed earlier to find the least cost way of meeting the new project deadline, and then come back whenever you are ready. Okay. So this problem is it has very similar situations as our previous example, right? So Dusty learned that one of his competitors' studio blockbuster movie is going to hit the market about the same time when his movie is to be released, right? So his studio decided to accelerate production of their movie by allocating more funds to meet the new deadline of 14 days, 14 weeks. Okay, so now let's using this given table values, let's compute the unit crash cost for each activity, right? Which is a unit cost of reducing the duration of each activities down here, okay? So, okay, let me use Microsoft Word for that. Okay. So basically the unit crash cost, the weekly unit cost of reducing the duration of activity, let's say activity A first, okay? That's gonna be $36 minus 24 over 5 minus 3. You know what I'm doing? So what is the numerator? 36 minus 24. So I got those values from here, 36 and 24. That's the crash cost minus the normal cost. So that's the changes in the amount of cost, right? So that's the changes in the amount. Let me disable my camera again. So changes in the amount of cost over the changes in the amount of time. So 5 minus 3, that's going to be the denominator down here. So I do say that's the change in the amount of time. Okay. So that's the unit crash cost, I call it, okay, of reducing the duration of activity A. Okay. So how much is that? That's going to be 12 over 2, which is equal to 6. Okay. So here, let me resize the table a little bit. Yeah, that. And then what I'm going to do is create one more column. Doesn't allow. Okay, let's see. So I'm going to create this column. So I'm going to call it unit cost of reducing the duration of each activity. So that's the unit crash cost. Let me change the color. Let's use red. So I'm going to call it unit crash. Oh, sorry. Unit crash cost. That's going to be in this last column. And for the activity A, that's going to be 6. So I need to do the same thing for, excuse me, activity B. That's going to be 25 minus 13 over 3 minus 2. That's 12, right? So we have 12 for activity B. And what about C? For C, it's going to be 29 minus 21 over 4 minus 2. How much is that? That's 4, right? So we have 4 down here. And how about D? D is going to be 50 minus 30 over 6 minus 3. How much is that? 20 over 3, right? So that's like 6.67, right? So we have 6.67 for D. So if you continue on this for E, that's going to be 36 minus 26 over 5 minus 4. So that's 10, right? 10. And for F, 57 minus 35 over 7 minus 4. How much is that? 22 over 3. So it's like 7.33, right? And for G, similarly, 53 minus 30 over 9 minus 5. Which is that? 23 over 4. Okay, so that's gonna be 5.75, right? Okay. Lastly, H, that's gonna be 51 minus 35 over 8 minus 6. How much is that? That's 8 for H. So we're gonna use this unit crash cost as the objective coefficient values for our LP model, right? So our objective function is to minimize the additional cost incurred in crashing the project, right? So that's gonna be 6 times RA plus 12 times RB, 4 times RC, 6.67 RD, 10 RE, 7.33 RF, 5.75 RG, right? And 8 times RH. That's our objective function. Okay, now we need to think about what constraints that we need to consider, right? So according this table, we can see that by allocating these additional funds to an activity, the activity duration, let's say for duration of activity A can be reduced by at most how many days? At most 2 days, right? That's 5 minus 3. Sorry, at most 2 weeks in this case, right? 5 minus 3 is going to be 2 weeks. So we have an inequality constraint, like R sub A is going to be less than equals 2. And this value 2 is from 5 minus 3 down here. So we have an inequality constraint for every activities A through H down here. Okay, so similarly, R sub B is going to be 3 minus 2, which is 1 week, right? R sub C is going to be 4 minus 2, which is 2 weeks, right? So R sub C less than equals 2. Likewise, R sub D is less than equals 3. R sub E less than equals 1. R sub F less than equals 3. R sub G less than equals 4. R sub H less than equals 2. Right? And also for every precedence relationship, we need to have an inequality constraint, right? So did we ever draw the network diagram? No, we didn't. Okay, so based on this precedence relationships, let's draw the network diagram. Did I get this? Okay. Insert pages. What is that? No. I want. It's wrong. Okay, so I've inserted another page. So let's draw the AOA network diagram. So both activities, A and B, doesn't have any predecessor. So I'm gonna have A, duration 5, and then I'm gonna have B, duration 3, and then C has predecessor, which is A. So I'm going to have C up here. And D has also predecessor A. Okay, I got it. So if I have another event down here, then I'm going to make a connection to here, and I'm going to have activity D. And E is going to be up here. This is going to be our F, G, right here, right? So that G has two predecessors. Those are C and E. And I'm going to have H that has two predecessors, D and F, okay? Like that. So I can put 1, 2, 3, and 4, 5, 6. It's fine. Yeah, the beginning node can be 1. It doesn't necessary to be 0 all the time. So let's just leave it like this. And so we're going to have D is 6, right? And E is 5. F is 7. G is 9. And H is 8. That's from the normal time, right? Yeah. Okay, so that's our AOA network diagram according to the precedence relationship. So for each precedence relationship, we need to have an inequality constraint, right? That has the general form of y sub j has to be greater than or equal to y sub I plus d sub ij minus rk, right? Do you remember, right? So for example, here, if you consider arc 1, 2, then you're going to have y1 is greater than equal to, sorry, y2 is greater than equal to y1 plus 5 minus r sub a, right? Up here. Because in this case, the activity A has a duration of 5 minus r sub a now, right? So here, y sub 1 plus 5 minus r sub a is going to be the completion time for activity A. So for every directed arc, we need a similar inequality constraint like that. Okay, so that's gonna be y sub 2 is greater than equal to y sub 1 plus 5 minus r sub a, right? Y sub 3 greater than equal to y sub 1 plus 3 minus r sub b, right? And then y sub 4 greater than equal to y sub 3 plus 5 minus r sub e and y sub 4 greater than equal to y sub 2 plus 4 minus r sub c, right? And then what? Y sub 4, sorry, y sub 5 greater than equals y sub 2 plus 6 minus r sub d, y sub 5 greater than equal to y sub 3 plus 7 minus r sub f, right? This is 7. Likewise, for arc 4, 6, it's going to be y sub 6 greater than equal to y sub 4 plus 9 minus r sub g, right? So last one, for arc 5, 6, y sub 6 greater than equal to y sub 5 plus 8 minus r sub h. Okay, so we need this 8 inequality constraint, right, for each arc in this AOA network diagram. And then what next? Also, we have to make sure the new deadline of 14 weeks has to be met. So y sub 6 minus y sub 1 has to be less than equal to 14, right? And we also need to consider the sign restriction, right? So for every r variable, r sub k, we need to add the negativity restriction. And for every y variable, unrestricted in sign will be added, okay? So let's put them in the Lingo model, okay? So I'm gonna open the new window. Make sure, okay, we need to use Lingo input because it does say Lingo model, right? So I'm gonna use Lingo input for that. We'll bring in here. Okay. So that's going to be minimize equals 6 times RA plus 12 RB 4 RC 6.67 RD 10 RE 7.33 RF 5.75 RG, right? And 8 times RH. And I forgot to include asterisk as the multiplication symbol. Let me just change the line here. Yes. Okay, yeah. And then don't forget semicolon at the end of objective function. And then RA has to be less than equal to 2. RB less than equal to 1. RC less than equal to 2. RD less than equal to 3. RE less than equal to 1. RF less than equal to 3. And RG less than equal to 4. RH less than equal to 2. Okay. Okay. And then our next constraint set, which is this, right? So y2 is greater than equal to y1 plus 5 minus RA. Y3 is greater than equal to y1 plus 3 minus RB. Y4 is greater than equal to y3 plus 5 minus RE. Y4 greater than equal to y2 plus 4 minus RC. And here, let me put them in here. Y5 greater than equal to y2 plus 6 minus RD. Y5 greater than equal to y3 plus 7 minus RF. You're almost there. Please pay attention. It's greater than equal to y4 plus 9 minus RG. Finally, y6 greater than equal to y5 plus 8 minus r4, rh. What is that? And then y6 minus y1 has to be less than equal to 14 weeks. That's the new project deadline, right? And then we need to add free variable restriction for every y variables, right? So add free inside parentheses, we need to specify each y variable. So y0 is the one. I'm going to copy this. 3. And then I'm going to just change this. 1, 2, 3, 4, and 5. Let me do this way. Four, and then can do this, right? Okay. So we can save some space. And I'm going to put ending mark here. Oops. And then I'm going to run it. So it looks like we have an optimal solution. Right away. Okay. So the optimal objective function value 65.5 tells you that the project deadline of 14 days, the new project deadline of 14 days can be met for an additional cost of $65.50. Okay. And here we have the optimal solution. So let me copy this and paste down here. Okay. So this is the original network diagram, right? And then so our optimal solution suggests that the activity A, the duration for activity A has to be reduced by 2. So it's going to be 3, right? And for activity B, the duration has to be reduced by 1. So it's going to be 2. And then C remains the same. D will be reduced by 1 week. So it's going to be, how much was that? was 6. And then 6 minus 1 going to be 5. Okay. And then E is going to be remain the same. F will be reduced by 1 week. It's going to be 6. And F, no, F we did it. And G will be reduced by 2. So it's going to be 7. And H will be reduced by 2. So it's going to be 6, right? Okay. So after reducing the durations of activities A through H by this given amount, so we obtain the new network pictured like this, okay? So based on this revised network diagram, let's get the dual LP model. So our objective function is maximization problem, right? Because we want to get the longest path from the beginning node, which is node 1 in our case, to the ending node, finishing node, which is node number 6. So that's going to be max equals 3 times x12, 2 times x13, 4 times x24, 5 times x25, 5 times x34, 6 times x35, 7 times x46, 6 times x56. Okay, again, I need to include asterisk symbol here. Okay, now our objective function is done. Next, the constraint set. So the left-hand side is going to be inflow minus outflow, right? Then right-hand side value becomes net flow. So for each event, we need to do this, right? So for event number 1, it's going to be x12, x13 equals -1, because event number 1, node number 1 is the supply node. And event number 2, we have x12 minus x24, x25. 0.25, right? Equals 0. For event number 3, x13 minus x34, x35. Event number 4, we have 2 inflows, x24, x34, and then only 1 outflow, x46 equals 0. And event number 5, we have 2 inflows, x25, x35, 1 outflow, x56, right? Equals 0. And for event number 6, we have 2 inflows, x46, x56, but there is no outflow. And node number 6 is the demand node. So net flow value must be equal to 1. I think that's it, right? Now we got the optimal solution here. Okay, so here with this updated network diagram, we are able to complete our project within 14 weeks, right? And then down here, this provides you the critical path. That's going to be 1, 3, 5, and 6. That's our critical path. So 1, 3, 5, 6. So the critical activities include B, F, and H, right? And the project can be completed within 14 weeks. This new deadline can be met for a cost of, how much was that earlier? Here, $65.50. Okay. Okay, so I think that's it. Yeah, I think that's all for today. Okay, so next time we are going to talk about PERT just briefly, and then we're gonna give you a small example for that. That will conclude the our discussion on the project management. And after that, we are moving on to the new topic. Okay. Okay. Thank you. We'll see you next time. Bye-bye.